Good afternoon, everyone. Let's all welcome Ben Bangert, who's going to talk to us about distributed coordination with Python.
Afternoon, everyone. We're going to go pretty fast here because we've got a lot to cover, so I'll just dive right in. First, it's probably easiest to explain distributed coordination by, well, what is not distributed coordination? So people are familiar with things like distributed databases. These are your big ones, Cassandra, Rayek. People are familiar with distributed computing. They know that they use Hadoop, and there's HDFS and all these other things built on top. And if you have large enough needs, you might have needed event analysis, stream processing, things like that. Storm is one of those tools. But when you look at all of these tools that do these various tasks, many of them have one need in common. You can't really do a lot of these things unless you have somewhere to actually coordinate. And the one that really is the most important for a lot of these when it comes to that coordination is a project called Apache Zookeeper. Zookeeper is a centralized service for maintaining configuration information, naming, providing distributed synchronization, providing group services. So this sort of encompasses quite a bit of things. Zookeeper, the project itself, is used inside a lot of those other tools. So Hadoop uses Zookeeper, Apache Mesos uses Zookeeper, Storm uses Zookeeper. Anytime you get a sufficiently large enough system, it seems sooner or later they will use Zookeeper. So first, a few things about it. To coordinate information between a whole bunch of nodes, you generally need somewhere that they all agree on is actually giving you correct information, which means it needs to be consistent. So for those familiar with the CAP theorem on consistency, availability, and partition tolerance, it is consistent and available. It's definitely not partition tolerant. People should keep that in mind. I say mostly here because there's a new feature in the latest Zookeeper that actually allows you to connect to a partition node, and it will tell you that it's partitioned. And you can still read data, but obviously it's no longer possibly consistent. Zookeeper itself stores all of its data structure in what it calls Z nodes. Now, this is a hierarchical structure, so it looks sort of like that. You have some nodes, they all go down. Each one is named, it has a path to reach it, and every node can hold some data. And the node itself can't hold that much data. It really can only hold a string. So you can serialize the JSON if you wanted to store something larger inside a node, but essentially you don't want to store too much in here. It's distributed. So this is really important, of course, for an available system. You can go ahead and blow away nodes and everything runs fine, and ops people are not woken up. Ops people generally enjoy not being woken up by pagers, so that's always very useful. It's session-based. This is a little different than some other distributed systems. Your client has to maintain a connection to Zookeeper the entire time. If it does not have the connection, then its session is lost. These are persistent sessions, so there's a heartbeat that's used, and they talk back and forth. The other thing that's very important and useful in Zookeeper is that you have what they call Z-node watches. Essentially, these are push notifications of changes. So if you're interested in knowing when a specific node in that structure that Zookeeper is managing has changed, you can register a watch and it will tell you. And this is done on a push basis. It's going to be very useful if you're storing configuration information in those nodes and somebody changes the information. Now everybody that's connected immediately knows about it and can take action. This is generally used in larger systems when they need to determine, oh, did the master fail? Well, who's the slave now? Well, having an automatic protocol that all of this can be agreed on is really, really useful. And having them know about it as soon as possible is also very important when you have master-slave issues. There's two other special characteristics of Z nodes that will come up, ephemeral and sequential. And I'll go into a little bit more about those a little later. So now that we know what we could actually use, Apache Zookeeper, what do we use to talk to it within Python? There's really only two choices at this time. If you're using Twisted, use TX Zookeeper. If you're not using Twisted, if you're using G-Event, any of those kind of things, you can use Kazoo. Kazoo is a relatively new client in the past 6-8 months or so. It originates from a whole bunch of different projects, And actually, they all merged into a single project for the most part. One of the nice things in the Python community is on occasion, instead of having 10 libraries to do the same thing, we actually can get one library that does everything and makes it a little easier for people. So the unified client works with gEvent. You don't actually have to monkey patch anything, so I don't know if people have used gEvent and had issues with the monkey patching that it does. This actually works directly with gEvent, so that's nice. And it implements the wire protocol directly. This is actually really important because the general way before Kazoo that people would use Zookeeper is with a C extension. And having a C extension crash your Python process with a seg fault is never fun. It's really easy to use. Here's what some Python code looks like that actually talks to it. Just import a client and you go ahead and start talking to the client. It runs in a separate thread, so once it's started up, it'll go ahead and manage its session for you, so you don't have to worry about that. It'll notify you if you're curious about when certain things happen in the session, so if you're curious when your connection is lost, that's very important to know. It will tell you, so it has a sort of a callback style. You can register functions and it will tell you when they change. So how do we actually do the coordination factor with Zookeeper? Well, the first thing that people generally want to do when they use Zookeeper is store configuration information. You want to have a whole bunch of nodes in a large system, and they all need to talk to certain other people, or they need to know who's the master for this task, where do I find the Redis service that has the pub sub, or where do I find the RabbitMQ broker. It's really useful to have a central spot that configuration is stored that can be changed easily. And it's not hard-coded into INI files or Django settings or all of these things. There actually is another project that will load your configuration information for Django straight out of Zookeeper using the Kazoo client, which is extremely useful because then you don't have to have it hard-coded and rolled out to all the nodes whenever something changes. So generally, if you're storing configuration information, you can organize it in the node structure, so you can use sort of paths to organize database settings and where your RabbitMQ cluster is, all that kind of stuff. And then, of course, if things change, you want to know about it, so you set watches on nodes. So simple little example, you want to have a function. You want to know when has something on this path changed. You want to know what the new data is, and maybe you want to know if what the version is. So you register a callback like this, it tells you everything, and you're set. Another common example that a lot of people are interested in is when you have a whole bunch of nodes in a large distributed system, it's good to essentially have a meeting place. It's one thing when everybody knows who the other party is. You can use something like ZeroMQ because everybody knows who the other IPs are. In a very large distributed system, especially if it's coming up and down, like in the cloud, you don't know what all the IPs are in advance. Things just come up and they go down, and they need to have a place where they can all meet. So party membership helps you out with that. They can all go, okay, well, I need to meet all the other nodes in this cluster that are doing this task. So you can arrange a meeting place in Zookeeper, and they can all go there and find out who else is around. If you need to elect a leader, like only one person is allowed to sort of lead whatever's going on with this process, you can do that. There's recipes in Kazoo that make it really easy to do that kind of task, so they can all come to agreement on that. And then, of course, the capabilities change a little bit when we introduce the concept of ephemeral Z-nodes. So ephemeral, of course, they're sort of there only for a little bit. They're not there forever. In the Zookeeper world, this means that when you create an ephemeral Z-node, it's only there as long as your session is there. If your client dies and doesn't come back within a timeout period, Zookeeper automatically destroys that node, and it's no longer in the system. This is really useful for determining when nodes, of course, have left. Or if somebody's going to acquire a lock, which we'll talk about in a little bit, knowing when they no longer have the lock. The only special trait that's important about ephemeral Z-nodes is that they can't have children. Essentially, that means that tree structure you saw earlier, you can't have more of them underneath these. The other important one when we want to make larger or higher level primitives on top of Zookeeper is sequential Z-nodes. You get to supply a node name when you create a node, and you get back the same node name that you had, except it appends some information on the end of it. It tells you what the sequence number is of your node. So essentially what Zookeeper is doing is you have a cluster of machines that are participating in what they call a quorum. Now, one of them is technically the leader. So when new commands go in, they all get routed to the leader, and the leader has to put all of these instructions together in a very ordered way, and then it processes it one by one. This is how it's fully consistent. So no matter which one in the cluster you read from, they all agreed on the order of operations as they went through. So you have a consistent picture of what's going on. Now, utilizing this with the sequential nodes, when it goes through, it just tags them with the next node number. So the first one gets 0001, 0002, 0003. And it just goes on, up and up and up. And of course, you can combine this with ephemeral. So here's a little example right here, ZK using the Kazoo client. Create a node called /node. So it'll make one of those nodes under the root of the tree. We want it to be ephemeral, and we want it to be a sequence node. So we can go ahead and create one of those nodes and put it there. This example is technically slightly incomplete. You do need to give it some data to actually store there. If you don't care about that, you can just say, you know, a null byte or none, and there won't be anything stored there. That's fine. So how do we make something interesting with these capabilities? And this is where it starts getting a little bit more interesting for Zookeeper. With these primitives, we can build more advanced data structures and coordination mechanisms on top. We can implement things like a lock. We have a few basic steps to creating a lock. This is generally what will be implemented by your library. So if you're using Java, you might want to use a library called Netflix Curator, but of course everybody's here is using Python, so Kazoo has a lock for you. The basic steps work like this. You create a lock parent node. So essentially you're going to create one node that doesn't have anybody underneath it. And this is what the lock is that everybody's going to agree on. So if the lock is called, you know, Fred, then everybody's going to lock the Fred resource, whatever that is. So we create the lock parent node if needed. We create the ephemeral plus the sequence node, and we store it underneath. And we get a name back for it. We then ask Zookeeper, give us all the children that have this and what all the names are of all the nodes. And then we sort this list by the last portion. These are the numbers, the very last bit. Now, all of our clients know how to sort, and we'll just go to sort on those numbers in the very end. So we sort on all the ones in the very end, and if yours is the one that's in the very front, you have the lock. This works really nicely because we have a consistent operation. Since everything goes through in a consistent order and we get back the list and everybody sees the same list, more or less, they know that if you have the lowest one, you have the lock. So what do we need to watch out for when we start writing larger distributed systems? Well, first, we definitely need to avoid the thundering herd problem. So use watches only when we absolutely need them. We can't use these too often. Even though we might have a large cluster, if you're watching a whole bunch of nodes and they all wake up at once, that's going to be a lot of traffic for Zookeeper, and you generally want to minimize that as much as possible. It really helps with the system. Of course, when the node that we have in our list from the lock is not the lowest one, there's a question, how do you know when you should look to see whether or not you are now the lowest node? And the answer is pretty simple. Once we have that sorted list that we got back of all the children that were underneath our node in Zookeeper, if we're not the lowest one, we just set a watch on the one in front of us. This way, everybody, you could think of it sort of like a queue. Everybody's in line, the guy that's in the front has the lock. So everybody really only needs to pay attention to the person in front of them. You don't need to watch the guy at the very beginning, so everybody's not watching the same guy, everybody's just watching the one in front of them. So Zookeeper only tells the next person in line, hey, there's nobody in front of you anymore. And everybody can sort of shuffle along, and it also makes sure that when you ask for a lock, everybody gets a lock in order. So the most important thing to realize is that failure does happen. Everything will die all the time. It's not fun when things die, especially in large distributed systems. Nodes come up, nodes go down. Bad things generally happen. The best thing that you generally want to do when these type of things happen is you want to fail fast and fail completely. So earlier I talked about you have a session with Zookeeper. Now, when your session dies, you get notified by the client. The client tells you, hey, I'm no longer either connected to Zookeeper, because it's gone for whatever reason, or your session has expired. Now, if you remember that when we make a lock, it's an ephemeral node. So that node goes away if our session is expired, which means that if you had a lock, You no longer have the lock anymore. You might have 10, 15, 20, 30, you could have a lot of things going on at once. And if your session expires, all of those nodes that you created that are ephemeral are all gone. So whatever was being synchronized, you're most likely not a part of that process anymore. So the easiest way that the Zookeeper documentation recommends, and I would also recommend, is sysexit your program. Just die. Die completely. Exit as fast as possible. Let supervisor or your process manager pick up the slack, restart your process, and then you start over again. This is because generally when your process starts up, it has to put everything together and get to a state. It's easier to do that once at the beginning than to write recovery code that tries to figure out what the current state is and then get everything back to the same state again. So always fail completely and then just start over again. Always include jitter. If you write a large enough system, maybe your ops people have mentioned that you should introduce jitter to some of the clients sometimes. Jitter essentially means that rather than everybody retrying operations in a network environment, oh, retry this, sleep 1 second, try again. Let's do exponential, sleep 2 seconds, sleep 4 seconds, sleep 6 seconds. Well, if 1,000 nodes become disconnected and then 1,000 nodes get reconnected and they're all doing that, all of them are going to slam the servers once, then twice, then 3 times, and those poor servers have to respond to everything, and ops people are woken up and very unhappy. So we include some jitter. Just a little bit, it doesn't need to be much, as long as we can sort of stagger out randomly when all of those clients reconnect. Kazoo does this automatically in its connection and in its retry operations. So when you ask Kazoo to go ahead and do a command for you against Zookeeper, tell me what nodes are here, tell me the data of the node, one of these kind of operations, it will include jitter automatically for you. So this is really useful. If you're writing other systems that need to talk to central servers, it's also good to always introduce jitter. Staggering out those connections definitely makes things a lot easier. So with Zookeeper, you get several basic operations. You get essentially CRUD. You can create nodes, you can read nodes, you can update nodes, and you can delete nodes, of course. And when you need to update nodes, you have some basic operations. You can say, oh, well, I want to update this node, but only if the version is still this version of it. Zookeeper keeps information about what version of the node it is. So you can go ahead and say, oh, well, I only need to update it if it's this node. So that way you get very consistent ways to update information about this. And I have a few extra minutes than I thought, which is great, which means that we can talk about one other thing. Party membership. So a lot of times in a large distributed system, this is going to be slightly different, you have a set of restricted resources. Only 5 things can go ahead and use this at once. Well, we have a recipe that helps you out called a set partitioner. You can give it a set and determine how many people can go ahead and work with that, and then they can divvy it out. It's quite a complex algorithm, and there's a recipe inside of Kazoo that helps you out with this. If you're curious about using Kazoo and what kind of recipes are available, we have a lot of API documentation for you. It makes it really easy to go ahead and use it. We have barriers in case you want to go ahead and determine who's allowed to access something at once. Or if you want to determine, you want to do basic counters. I don't necessarily recommend using counters in this. It's very expensive. You have barriers. If anybody hasn't used a barrier before, it's useful if you need to have a whole bunch of nodes in a cluster all wait for a certain specific activity to complete before they proceed. So you essentially set up a barrier, you wait until everybody says, I've done this part of the chore, and then everybody goes on to the next step. You have basic elections. These allow you to decide who's a leader. So all of your nodes could come together, decide who's a leader, and move on. You have a lock. And inside of the lock, we also have another one that's more advanced. Sometimes you need a distributed semaphore. So we have a semaphore in there as well. There's a party, there's a basic queue, and then of course we have watchers for watching nodes. There's also a testing harness, which makes it a little bit easier. And generally, if you're going to be working with Zookeeper, I would highly recommend using Kazoo. Thank you. I think we still have a few minutes for questions. Awesome.
Hi. Can you talk a little bit about the wire protocol that's used?
Sure. So Zookeeper implements a binary protocol. Zookeeper is a Java application. And the official recommended clients for the longest time for it was essentially any language like Ruby and Python would use the C binding. The C binding unfortunately had a lot of problems, so we used the Wire protocol. So the Wire protocol for Zookeeper is not actually documented, which is really fun when you're trying to implement it. Zookeeper uses a system called Jute, and it generates the protocol as appropriate. So their documentation is the code, and when it's all generated, usually very inefficiently for Python, of course, they tell you go ahead and that should be fine. So it's a simple TCP protocol. It uses, I think, what is generally referred to as sort of the Plan 9 protocol, where it sends a header packet and then some of the data on it. It's implemented as a single thread right now in the newest version of Kazoo, which I'd recommend people trying out the 1.0 beta. Hopefully in the next week or two, we'll get closer to having the 1.0 completely done. Generally, it just implements, it's binary, does some basic packing as it goes back and forth. It does support Python 3, so if you want to use Python 2 or Python 3, you can do that with Kazoo. And we found that implementing the Wire protocol directly has had very little cost, if any, versus using the C binding, just because of all the stuff that needs to go back and forth and talking to that.
Does the Zookeeper protocol have any authentication or ability to control who can talk into the cluster or on
Yes.
these nodes?
Yeah, so all the nodes have ACL information on them. So they have access control lists. You can also essentially CH root client access entirely. So if you're using multiple different clients and they're only allowed to see certain portions of the tree, you can CH root them into that portion of the tree. It supports SASL, and then it also has a basic digest auth mechanism. And those permissions can be attached by the owners of the nodes when they're created, so you can say who can read it, who can create them, who can update them. It gets fairly fine-tuned on the access control.
Can you describe a little what a typical Zookeeper deployment looks like? Do you have dedicated Zookeeper servers, or do you run it alongside your application servers?
Yeah, so generally you're going to want to do servers that are dedicated to the task. Zookeeper stores everything in memory. But it is reliable. It writes to files, so you can restart them, and if they all go down at once and they all come back up, that's fine. So it is storing to the file system as well. Due to how it stores to the file system, though, to make sure it's fast, you want to make sure you don't have contention on the drive that's storing the data. So they generally recommend, when deploying Zookeeper, to have dedicated nodes for it. You want at least 3, because you want to have an odd number over 2, of course, so that you can lose 1. I would generally recommend having no less than 5. It's because, of course, if you have 3 and you have to take 1 down for maintenance, now you have no redundancy whatsoever until that 1 comes back. So if another one dies, then there goes the Zookeeper cluster. But yeah, have them dedicated to the task, and then have 2 drives inside, and one of them should be dedicated to the essentially the log file to make sure that it doesn't slow down. And you, of course, want to ensure that the Java process does not swap, because if that swaps, since all the structures are in memory, that would really kill performance. Especially since your writes do not scale linearly as you add more nodes. They can actually slow down once you go past about a dozen or so. And this is because everything, as I mentioned earlier, has to go through a single node to get the consensus on what operation applied in what order.
Out of curiosity, are there any alternatives to Zookeeper?
Yes.
For people who don't work in Google?
For people who don't work where?
Google.
Google. So Google uses Chubby Lock, I believe, which does most of this task. Zookeeper is sort of what the rest of us use, since we don't work at Google. And the lucky people that work at Google just go, why is this a problem? You just use Chubby Lock. And I'm like, yeah, thank you. There is another alternative out there written in Go called Doozard. And I'm not sure what the status of it is. It's not necessarily at the moment appropriate for some of this stuff because it doesn't have sessions. And if you don't have the sessions with the ephemeral nodes, then if you have a client that had a lock die, when does that node saying that he has a lock go away? And then all the other clients have to become a lot smarter to start going, okay, well, he hasn't touched a node in this long, or you have to make up yet another algorithm. So things get a little bit more complex. There's some forks of Doozerd, which are adding some of the session things. So at some point, that might get there where it might be a better choice than Zookeeper, in which case I'm sure we'll very easily adapt Kazoo to talk to Doozerd as well.
Hello. That was somewhat my question. How would you sell me Zookeeper instead of a trivial solution like Redis, which most of the, like blog shops and stuff use for most of the things?
Okay, so for Redis, the main issue is how good are your ops people and how much do you like them? So, I mean, you can't really, there's Redis cluster which is coming along, but you can throw up 15 Zookeeper, 15 node Zookeeper, and until you lose more than 7 nodes, ops people aren't calling you. And that's really nice. Ops people also really, really appreciate that. Some people have really good ops people, and they're just like, well, we just have a whole bunch of Redis things, and our ops people juggle them around, and if they have to rebalance some of the data, okay, maybe they hate you then. But overall, it doesn't seem that bad. And, if you're going to be sharding your data, that can make it sometimes easier, but of course, if you lose that Redis node, Redis doesn't have ephemeral nodes. So if you have a client die, when does the lock get released? So those things become really important. Having that taken care of for you by the Zookeeper process simplifies a lot of the logic involved. And having simple logic involved when you're using a distributed system, especially when you have all sorts of crazy stuff happening, is really nice, because almost always, having it work properly is always better than having it work fast.
Hi, Ben. I was wondering how interested anybody would be in like a pure Python implementation. There's certain projects out there that I think could use better coordination and self-healing, but might be reticent to include Java as a dependency, for example.
Right, so is that something like, what are you thinking of re-implementing Zookeeper in Python?
I hate reinventing the wheel, but it's tempting.
So I had actually, when I went diving into it to look at the protocol and see how it was implemented and watch everything going back and forth, I told the people in the Zookeeper community about this, and they said, that's great, can you document the protocol for us? And I read through a lot of the code, and I was like, no, I don't really want to document the protocol. I mean, I might at some point, but I was looking, since I had already got into the protocol layer, oh, well, PyPy makes everything fast. I'll just re-implement the entire thing in PyPy, Python, and run it on PyPy, and then I'll have a server and run that directly. I had looked at that several times. Generally, the reason that I get leery of doing that is, and goes to a lot of these consensus things, is a set of algorithms that people can look up on Wikipedia. They're great fun to look at. Paxos algorithms. And the one thing that pretty much everybody I've ever talked to in the distributed world says is you do not want to implement Paxos algorithms any more than you want to implement crypto yourself, which is another thing that nobody should ever implement if you can avoid it. So I haven't wanted to get into it too much just because I don't want to get into exactly how that works. But I've looked at it, and I think it would be worth considering. I mean, there's a lot of code in there for the Zookeeper server that definitely would be a lot simpler. Well, even if they rewrote a good chunk of it in Java, it would be simpler. But the current one has what you might call a lot of battle scars in it, and you could see the battle scars, and it took a beating, that's for sure. So I don't think people would be adverse to having a better implementation. I guess that's all of our time. Oh, do we have any more? Thanks.